Welcome back, everybody. Mr. Johnson here once again. It is still Sunday, September 20th. Been recording now for a couple of hours. It's 12:18. Hoping to be done by 1 o'clock so I can watch the Seahawks while I'm doing a bit more schoolwork. We are on page 134 of your ebook. We're on section 3.4, molar volume. And here we go. So the first thing I'm going to point out is this sentence here, which says the molar volume of a substance is the space occupied by a mole of its particles. As its name implies, it's the volume of a mole. Much like molar mass is the mass of a mole, molar volume is the volume of a mole. Further down it says liquids and gases are more frequently measured by volume than mass. Liquids and gases are more frequently measured by volume than mass. And a substance's molar volume allows you to convert the volume of a substance into its number of moles. What we're going to find through this lecture is that for liquids, we use density to get from moles to volume or volume to moles, along with molar mass in there. But for gases, we're going to have this value that's going to come our way. It comes from Avogadro's hypothesis that allows us to convert from moles to volume of a gas or volume to moles. Later, when we get to our gas law unit, we're going to find another way to do that using the ideal gas law. But for now, it's this value that I'll be revealing to you in a moment. All right, so I've just scrolled down. We're still on page 134 of our ebook, looking at this section called the molar volume of gases. Well, here's Avogadro making an appearance in our book once again, who came up with this hypothesis. Avogadro hypothesized that equal volumes of different gases measured at the same temperature and pressure have equal numbers of particles. And modern chemists still refer to this as Avogadro's hypothesis. And it's a really important concept that we use regularly in chemistry. The idea is that the volume that a gas occupies is based almost entirely on how far apart those gas molecules are from each other. We'll talk more about this later in our gas law unit. Gas particles themselves, the size of an individual gas particle itself is so small compared to how far apart the gas particles are that the size of an individual gas particle itself doesn't really contribute much to the volume that that gas occupies, which means that it doesn't matter what gas we have. It could be helium gas or carbon dioxide gas or oxygen gas. If those gases are at the same temperature and pressure, even though those molecules themselves have different sizes, the spacing between the particles will be the same and they will occupy the same volume. And that's because the spacing of gas particles is a function of the temperature that those particles are at. The greater the temperature, the faster they're moving, the more they collide off each other, the more they spread out, and the greater volume they take up. So temperature affects spacing, and so does pressure. And if the gases we're talking about are at the same temperature and pressure, they will occupy the same volume. And that concept, again, is referred to as Avogadro's hypothesis. So as an example, 1 mole of any gas at 0 degrees Celsius and a pressure of 101.3 kilopascals. We'll talk about pressure later, units for pressure later, except that kilopascals is a unit for pressure, occupies approximately 22.4 liters. One thing I neglected to say earlier is that not only does the temperature and pressure of a gas affect its spacing, which it does, and its volume, but volume is also affected by how many gas particles there are. So if we've got a certain number of gas particles, 1 mole, at a certain temperature, 0 degrees Celsius, which is also 273 Kelvin, we'll deal with that later, and a pressure of 101.3 kilopascals, the volume of any gas, CO2, O2, helium, neon, is going to be 22.4 liters. So I've got a globe here because I'm not at school, and what I don't have is my molar volume box. But normally I hold up a cardboard box that has the dimensions pretty equivalent to the diameter of this globe. So if this globe were, were a square, were a cube, it would approximately be 22.4 liters. So if we pictured this globe as a cube, not a sphere, then imagining that we are at roughly 0 degrees Celsius, no, my home isn't that cold, and 101.3 kPa, which is pretty close to the pressure right now in this room, there'd be about a mole of gas particles in here. 6.02 times 10 to the 23, which again is a ridiculously high number of particles. Because we use and refer to this value often, 22.4 liters, coming from 0 Celsius and 101.3 kPa, there's a term to describe that temperature and that pressure, and it's called standard temperature and pressure, abbreviated STP. Standard temperature and pressure is 0 Celsius, or 273 Kelvin, and 101.3 kPa. I'm slightly annoyed it rounded it to 100 kPa here. There's other units for pressure that could be used instead of kPa, but for now we'll just stick with kPa. So again, standard temperature and pressure, STP, is 0 Celsius and 101.3 kPa. And while that's true, you don't really need to remember that right now. What you do need to remember, though, is that 22.4 liters equaling 1 mole of a gas is only true at STP. So unless a problem states that a gas is at STP, or 0 Celsius and 101.3 kPa, we can't use 1 mole equaling 22.4 liters. For now, though, the problems that we'll be solving that expect us to go from moles of a gas to volume of a gas will always be at STP, so we will be able to use 22.4 until we learn another way to do so. I've turned the page. I'm now on page 135 of the ebook, and I'm looking at this chart at the top of that page. This is the third time we've seen a chart like this. The first time was with 1 mole equaling Avogadro's number of particles. The second time was 1 mole equaling the mass in grams, meaning molar mass. And the third version of this, which we see now, is for molar volume. The equivalency that exists between moles and volume at STP is 1 mole equals 22.4 liters. And from that, once again, 2 conversion factors can be written, one the reciprocal of the other. Either 22.4 liters on top, 1 mole on the bottom, or 1 mole up top, 22.4 on the bottom. Once again, only valid or true at STP, standard temperature and pressure. So I've flipped my page. I'm on 136 of the ebook, and I'm first going to look at the wheel down here. Looks like another spoke of this wheel has been labeled. We've seen these 2 already, and that's the spoke that takes us from moles to volume. And we see here that it's molar volume that does that. And it would be the number of liters in a mole that would allow that conversion to occur. Again, at STP, it would be 22.4 liters per mole, but because this wheel is meant to be able to be used at any temperature or pressure, 22.4 isn't there to account for that it may not always be at STP, or standard temperature and pressure. So we're now going to go up to practice problem 1 on this page and figure out what volume of oxygen gas at STP contains 1.33 moles of oxygen. All right, so going from moles to volume, and unless we're told otherwise, we assume it's liters that we're going to. We could convert liters to milliliters in the end if we wanted to, but it doesn't ask us. So I've written 1.33 moles of O2 up top. I'm going to put a 1 down on the bottom, so I'm not tempted to put anything else there. And I know that there's 22.4 liters that equals 1 mole at STP. So I'm going to put 1 mole on the bottom so that moles cancels. I'm going to put 22.4 liters up top. And when I go to my calculator, I get 29.792 liters of O2. Need to round it to sig figs again. Both 1.33 and 22.4 have 3 significant figures. 22.4 isn't exact, that 1 is. So there could be times when 22.4 limits sig figs. In this case, both numbers do. So it's going to be 20. Ooh, I almost got excited to write a 9, but that 9's going to kick that 7 up to an 8. Never mind, I still get to write my 9. 29.8 liters of O2. Thought it was going to round up to 30, but it didn't. So I'm looking again at this wheel model on this same page, page 136, and I'm reminding you that we've always got to go through moles anytime we want to go from one unit to another. If you're starting with volume and liters and you want to get to grams, you first have to go through moles. So everything, once again, always goes through moles. So I've flipped a couple of pages. I'm now on page 138 of our ebook, looking at practice problem 1 on page 138 of the ebook. H2 gas is released from rotten eggs. What volume of H2 gas at STP contains 17 grams? So because it's at STP, we can use 22.4. So I've decided in advance that I know I need to go from grams to moles, because I've always got to go through moles, and then I'll go from moles to liters. And I'm using blue now. in anticipation of looking forward to sitting down and watching a little Seahawks. 17 grams of H2S on the top, 1 on the bottom, so I'm not tempted to write anything else there. I know that 1 mole of H2S weighs 32.07 plus 1.01 plus 1.01, so 34.07 grams H2S. And 1 mole of H2S has a volume of 22.4 liters at, of course, STP only. So when I go to my calculator, I get, and I realized I'd never gone to this mode. Hopefully you can see that a bit better now. 11.1769 liters, and with 2 sig figs, because of 17, that's just going to be 11 liters of H2S gas. Well done, folks. I'm proud of you. All right, we've flipped the page. We're on now 139 of the ebook, and I'm looking at the top here where it says molar volume and density. This is the last section. We'll be solving our last problem here together, so thanks for hanging in there with me today. Density, it says, is the amount of matter in a given volume of an object or material. In other words, it's the mass per unit volume. Mass per unit volume. And a common unit for density is grams per milliliter. If it's not a gas at STP, if it's a liquid, for example, and we know its density, we can go straight from mass to volume without going through moles, because density is the ratio between mass and volume. Density will take us straight there. Or we could go from volume to mass through density without passing through moles. It might be you have to convert from liters to milliliters first before you use the value for density to get to mass. But it's otherwise a one-step conversion, which again doesn't require going through moles. So I've flipped to page 140 of the ebook, and I'm looking now at practice problem 2 on page 140. Mercury, it says, has a density of 13.534 grams per milliliter at room temperature. What is the mass of 12.7 milliliters of mercury? We could do this algebraically. We could write the formula density equals mass over volume and plug in a density and a volume and get a mass and use algebra. But we want to avoid using algebra in here whenever we can. We want to use dimensional analysis to solve problems whenever we can. So I'm going to model this for you using dimensional analysis. So we could start by writing 12.7 milliliters in a DA box. But one thing I'm going to start to get us to be thinking about, and trickier to solve problems, is to ask ourselves, what unit in the end do we want? Because if we often think about what the outcome is, we know where to start. What unit do we want in the end? Well, we want a mass. We want a mass in the end. And if we're given a value in our problem that has that unit we want in the end, grams, somewhere in it, and we write that value at that unit such that the unit is in the numerator of a DA box, it's often an easy way to get to the end in problems that are trickier to solve, which I'd argue this one isn't, but let me just show you that. So I'm going to write 13.534 grams per 1 milliliter first. I know I want grams in the end, and if I find a way to get the unit grams in the top of a DA box first and cancel my denominator, I'll end up with what I want. So notice that I didn't write grams per milliliter like that and put nothing in the denominator. Rather, knowing that milliliter is actually in the denominator, I put it in the denominator of my DA box. So that's really important, is when we've got fractional units, to always put the unit to the right of the slash in the denominator of a DA box. All right, well, I want to be left with grams in the end. It means I need to cancel milliliters, so I put the volume of 12.7 milliliters. This is the volume of mercury. This is its density. I'm able to use these two values together. Milliliters cancels, and I'll be left with grams. And what I'm doing is multiplying the density by the volume. And density times volume is mass. But I didn't need to worry about that algebraically. Dimensional analysis did that for me. I could have written 12.7 first and the density second. It wouldn't matter. But I just wanted to show you how, if you know what your goal is in the end, what unit you want to get to, if you start by writing that unit in the numerator and canceling whatever else is there to begin with that you don't want, it's often a great way to get to your end if you're not quite sure how to get there. So unrounded, I get 171.88 grams with 3 sig figs. I round my final answer to 172 grams. Just want to say one more thing before we go. If the problem had given us a mass instead of the volume that it did, and the same density, 12.7 grams, same density, and had asked us for a volume, here's how we could think about it. Again, if we know we want to get to milliliters in the end, I said earlier that if we look for in the values we're given, the unit that we want, milliliters, and somehow write it in the numerator and leave it there and cancel everything else out, that's often an easy way to get to the final answer. Well, the density, 13.534 grams per milliliter, has milliliters in the denominator. And if I write it somehow to begin with in the numerator and get rid of everything else, I'll get my final answer. So I can write this density not as 13.534 grams per 1 milliliter, but rather I can write it as its reciprocal, 1 milliliter per 13.534 grams. It's just a different way of expressing density, the volume over the mass instead of the mass over the volume. And then, if I've got milliliters up top, I keep it. I just need to get rid of grams. I multiply by 12.7 grams. Grams cancels, and 12.7 divided by the density would be the mass, would be the volume of that mass. And same as last time. I could have started by writing 12.7 grams and written the density, but I'd still have to have the density the way I do now, with volume up top and mass on the bottom for the right units to cancel. That's it, folks. Enjoy the rest of your day. And I was going to send you off with a little Go Hawks, but then I realized that today's game is at 5 o'clock, not 1. So, not sure what I'm going to do for the next 4 hours, but I'm sure I can find a number of things to occupy myself. Take care. See ya.